So E0 is the cell potential when ion concentrations are standard, which is 1 mole per liter. So here for our zinc and copper ion cell, the standard cell potential is 1.1 volts. What happens to E when the concentrations change? Honestly, I can't remember what I was supposed to do here. The fact that there's a graph paper in the background means I'm supposed to write something. Let's see if we can figure it out together. Illustrations. So here we have the same two cells. What's different is the concentration. So here we have 1 molar zinc ion, 1 molar copper ion. Over here we have 0.01 molar zinc ions and 2 molar copper ions. So if we think of these half reactions, right, one's an oxidation, one's a reduction. If this product concentration goes from 1 down to 0.01, how would that affect this equation? It would shift to the right, right? The Chatelier's principle. And here, if we take the copper ion concentration from 1 and double it to 2, so we increase the reactant, decrease the product, we could kind of figure out, well, that means it's going to want to go more, right? And if we measure it, we see that this had a potential of 1.1. When we change the concentrations, the potential goes up. It becomes more spontaneous, 1.17. Okay, derive the relationship between standard cell potential and the cell potential. I screwed this up yesterday. Let's hope I can do it correctly. So what we have in common in these two equations is the standard free energy. So standard free energy equals this, and this is equal to standard free energy plus that. So I'm going to substitute this guy in for delta G0. So delta G is equal to delta G0, but I'm going to put this in there instead. Negative NF standard cell potential plus RT Q. Oops, not Q, natural log of Q. So what we end up with is this. This is a very important equation in electrochemistry, and it has a name. It's the Nernst equation. It's named after, a scientist. So this is the Nernst equation. E cell is the cell potential in volts. E0 cell is the standard cell potential in volts. So the standard cell potential is what you figure out by looking at the table of reduction potentials. N is the moles of electrons that are transferred in the redox reaction, and Q is the reaction quotient. Remember, the reaction quotient is calculated in the same way as the equilibrium constant, but it just uses whatever concentrations you have. So, determine the cell potential of an electrochemical cell based on the following two half reactions. And here's a note I gave myself. See standard electrode potentials on the next slide, so I don't go back, way back. Okay, so we have two half reactions here. This one has one electron, this one has two electrons. So these are not ready to be added together, are they? Because we're not going to be able to cancel out our electrons. We're going to need to calculate Q for the overall reaction, so we need the overall chemical equation. So here we are in the middle of a half reaction method of balancing a redox reaction. We've got these balanced for mass and for charge. Now we need to get the number of electrons equal. This one has 2 electrons on the right, this one has 1 on the left. And so we can fix that by multiplying the bottom equation by 2. So we put in a 2 there. That becomes a 4. This is a 2 and a 2 and a 2. Yeah.
Why wouldn't we break down like the reduction reaction even more, where it's like the hydrogens and the water?
That's a good question.
And the
So why wouldn't we break this down anymore? If you do break it down anymore and try to separate out the hydrogens and oxygens, when you go to balance the VO2 plus and the VO2 plus, you're going to end up putting them all back in. Yeah. So there's always going to be 2 half reactions, and there will never be a situation where I'm going to try to trick you with there being extra junk in there that you need to think, oh, we should take that out. Yeah, it's just face value. But that's a great question. So we need the cell potentials for these half reactions, which my little note says are on the next page, after we looked at the answer. Okay, so we've got the VO. There we go. Right here. VO2 plus going to VO2 plus. That's not confusing at all. So this is written in the same direction as what we have on the previous slide. So the standard cell potential is 1. So for this one, it's 1.00 volts. And then we're going to look for the nickel. Nickel is going to be down here, I believe. There it is. Nickel and nickel 2 plus. This one is written backwards from what we have on the slide. So I take the negative 0.23 volts and change the sign. So this, I'll just write it over here. This is plus 0.23 volts. So E cell 0 is equal to 1.23 volts. Everybody okay with that? What is N for this reaction? 2. 2 moles of electrons. So N is equal to 2. Okay, so now we need our Nernst equation. I don't trust my memory at all today. E cell minus 0.0592. Okay. So the cell potential is equal to the standard cell potential minus 0.0592 volts over N base 10 log of Q. Did I do that right?
Yes.
They've got like a frequency generator and it's just going up and up and up and up. I can't hear it anymore. Okay. It's just physics people doing physics things. It's fine. Okay, so we're going to substitute things into this. We figured out what the standard cell potential is. We figured out what N is, but we need to know what Q is. So we calculate Q from the overall reaction, which I forgot to finish. So I'm going to move this down out of the way. So I'm going to add these guys together. So I've got nickel. This is solid. So that's the left side of this one, and then I've got 2 VO2 space plus and 4 hydrogen ions. And then on the other side, I've got nickel 2 plus and VO 2 plus and 2 H2O. This is the standard cell potential. This is the redox reaction for that cell. So Q, I'm going to do Q down here. We're looking at products over reactants, and coefficients become exponents. So nickel and VO 2 plus, that has a coefficient of 2, so we square that. Are we going to put the water in there? No. Liquids and solids are left out because their concentrations don't change. So divided by nickel solid, that doesn't get included. And then we've got VO2 plus the coefficient of 2, so that gets squared. And then we have hydrogen ion to the 4th power. They gave us all these concentrations up here, so all we have to do is plug them in. So the nickel ion concentration is 2.0. VO 2 plus is 2 also, 2.0. That one's squared. Divided by VO2 plus, which is 0.01, squared. And the hydrogen ion concentration to the 4th power. So Q is 8 times 10 to the 4. Now we have everything we need to plug into the equation. I'm going to put in E, the standard cell potential, 1.23 volts, minus 0.0592 volts, divided by N. N is 2, because 2 moles of electrons are being transferred. Base 10 log of 8.0 times 10 to the 4. questions? That's a good exam question. There's a bunch of little steps in there, right? Each of the steps is not hard. Remembering how to put them all together can be challenging. And how do you get good at that? You practice, right? You do problems. I was talking to a student in the other section, and she has a great strategy. She's using her iPad to take notes on the lecture slides. But she still picks up the paper copy, because she says, what she likes to do is she likes to, after the lecture, she'll go through and try to do the examples in the paper copy without looking at her notes. I'm like, oh, that's pretty smart. You could also do it the other way around. You could take the notes on paper and then try to do the problems on a tablet.